Good evening, everyone. Today I will be addressing a critical challenge of our time: how to reduce the global carbon footprint of transportation, one of the largest contributors to global emission. Since 1960, global carbon emissions have skyrocketed by more than 50%, reaching an alarming 36.6 billion tons in 2023. Transportation alone is responsible for 22% of these emissions, with aviation and automobiles are the causes of this environmental crisis. In specific, a single gasoline-powered car emits an average of 4.7 metric tons of carbon dioxide annually. These numbers require the urgent adoption of sustainable alternatives to mitigate global emissions. Hydrogen fuel has emerged as a promising solution, capable of drastically reducing carbon emission while delivering high energy efficiency. Unlike gasoline-powered vehicles, hydrogen-powered cars only emit water vapors, making them far more environmentally friendly. Moreover, hydrogen fuel is remarkably energy dense, delivering nearly 3 times the energy output of gasoline. However, while hydrogen holds immense potential, its production methods such as steam methane reforming are still plagued by significant carbon emission. With this in mind, this raises an important question: how can the integration of carbon capture and storage and steam methane reforming optimize the carbon and energy efficiency of blue hydrogen production, thereby reducing transportation's carbon footprint? Accordingly, to tackle this question, we should begin with the evaluation of hydrogen fuel based on diverse perspectives, including its feasibility, market potential, carbon footprint, and alternative production methods. Hydrogen fuel has long been considered as a candidate for decarbonizing the transportation sector due to its energy density and scalability. Consider the numbers. Hydrogen fuel has an energy density of 120 megajoules per kilogram, compared to gasoline's 45.8. Such efficiency has already garnered interest with governments and automakers investing in hydrogen technology. For instance, countries like Japan, China, and the European Union have committed to developing 1 million hydrogen-powered vehicles and limit gasoline and diesel vehicles by the year 2030. Companies are also making starting such as the Hyundai's Tucson FCEV, which is this one, achieve 34% reduction in emission. Such milestone highlights hydrogen's potential to revolutionize sustainable mobility. Despite the application of hydrogen fuel in automobiles, hydrogen fuel is emerging as a transformative technology in the aviation industry. In November 2022, Airbus revealed a hydrogen-powered fuel cell engine for the zero-emission goals of aviation. This innovation is developed under AirSoc and can limit carbon emission while simultaneously increasing the scalability of power output. In addition, the Royal Netherlands Aerospace Center adapted a 600 kW system that increases the passenger size from 2-seaters to 200-plus seaters. Besides, even the European Committee proclaims to reduce carbon emission by more than 50% in 2025 and with a 75% carbon reduction per passenger kilometer, further highlighting the critical existence of hydrogen fuel in the aviation industry. Despite its promise, hydrogen production is far from carbon zero. The most widely utilized process, steam methane reforming or SMR, involves extracting hydrogen from natural gases. Although this method enables large-scale production, it is associated with severe environmental consequences. Specifically, SMR emits between 7.5 to 12 tons of carbon dioxide per ton of hydrogen produced. This is primarily due to the reaction between methane and steam, which generates carbon monoxide as a byproduct. Furthermore, SMR is an energy-intensive product. In fact, the energy demand of SMR is approximately 4 times higher than that of gasoline production, further diminishing its environmental sustainability. While hydrogen is positioned as a zero-emission energy source at the point of use, the environmental and energy inefficiency of its production through SMR remain significant barriers to its widespread adoption. Alternative methods of hydrogen production, such as electrolysis, have emerged as a promising solution to address this challenge of traditional processes. Electrolysis involves by splitting water into hydrogen and oxygen using electricity by using renewable energy sources that significantly reduces carbon emissions. However, despite these environmental benefits, electrolysis faces significant scalability challenge due to its reliance on renewable energy sources. The current global infrastructure for renewable energy remains insufficient to meet the substantial energy demands required for large-scale hydrogen production. Now, while the benefits of hydrogen fuel are undeniable, there is a critical gap in how we produce it efficiently and substantially. Currently, the predominant method is the more heavily relies on natural gases, resulting in significant carbon emission. That's hardly the green energy solution we need. On the other hand, alternative methods like electrolysis powered by renewable energy shows promising solution with minimized carbon emission. But here's the problem. Electrolysis struggles to scale up. The energy demand for large-scale hydrogen production simply cannot be met by current renewable sources alone. To determine the best hydrogen production methods, both environmental and economical factors must be considered. This research will evaluate its feasibility by using environmental life cycle assessment and the lived cost of hydrogen. Firstly, the carbon energy evaluation will be based on life cycle assessment LCA, which is used to measure the carbon footprint of hydrogen production. According to European Commission 2024 LCA report, key environmental factors including energy density and carbon emissions. Additionally, a meta-regression analysis from Science Direct 2024, which reviewed 100 LCA studies, further supports this research by providing extensive environmental impact data. Beyond environmental impacts, hydrogen must be economically viable. The integration of LCO calculates the average cost per unit of hydrogen by considering operational costs, capital costs, and maintenance expenses. According to reports from the International Energy Agency and Egypt Low Carbon Hydrogen Development Prospect, LCOH provides a strong foundation for cost comparison. Furthermore, Roland Berger, a global strategy consulting firm with more than 35 cooperating countries, published the 2024 Hydrogen Cost Report, gives a global perspective on hydrogen production expenditures. To bring all these data together, this research employs a cost-benefit evaluation metric that integrates environmental and economical data. This model is based on two key studies of hydrogen on the path to net zero and H2A light hydrogen model, in which this metric allows for a detailed comparison of each hydrogen production method by analyzing the energy consumption, carbon emission, cost per unit of hydrogen. These choices ultimately help create a more well-rounded practical, ensuring that this research findings to be both accurate and applicable to real-world hydrogen production strategies. Thank you.